Hello, grade 12s. We're going to do a worksheet for chapter 7 of the pre-calculus 12 together. So, the first question that we're looking at is to graph the exponential function y equals 1 over 2 to the power of x. Label all intercepts and asymptotes. So the first thing that we know is that regardless of the c value, or regardless of the base of this exponential function, is that the function always has the same y-intercept and the same horizontal asymptote. So obviously I'm going to start by drawing the, the axis. Axis will look like this. And then we're going to have the same horizontal asymptote at y equals 0. And then we're going to have the same y-intercept at 0, comma 1. So that's given. Now let's try to find some other points of this graph. I'm going to use a table of values. Well, first of all, I know that because my c value is less than 1 and greater than 0, my graph is decreasing. So it is called exponential decay. So I know that my overall graph will go downwards. But let's make a table of values. So first of all, let's start with, let's say, negative 2, for example. When x is negative 2, 1 over 2 to the power of negative 2 would be something like 2 to the power of positive 2 using the law of exponents. Right? When you have negative exponent, negative power, it gives you the reciprocal of the base. So that's equal to 4. So my value when x is negative 2 is 4. That's negative 2 to 4. And then when I have x equals negative 1, then 1 over 2 to the power of negative 1 will be just 2 to the power of 1, which is 2. So that's another point at negative 1 comma 2. And then 0 comma 1. And then let's go easier stuff now. When x equals 1, y equals 1 over 2. When x equals 2, y equals 1 over 4. And then I think the points can be connected easily now. Going from 4. During a pattern like this. Now, once again, when you're graphing the exponential function, what's most important are the intercepts and the asymptotes, but the other points don't matter too much as long as you definitely show either the decay or the growth. This one, it was a decay, so you need to show the decay function. The other points don't have to be so super neat. Okay, let's move on to the next question. This one, we're graphing the exponential function, negative 2 times 1 over 2 to the power of 2x plus 10. So we have some transformations here. Compared to the previous graph that we just had, the transformations that we have is, I think we can label this into multiple parts. The vertical, horizontal, SRT. Remember this table? This graphic organizer? First of all, there is a vertical stretch by a factor of 2, and there's a vertical reflection. There's a horizontal stretch by a factor of 1 over 2. And then we do not have a horizontal reflection. And there's no horizontal translation, and there is a vertical translation by a factor of 10, by 10 units. So why don't we start by putting things on the axis first. We could just make a new table and graph it as it is, but because we're learning about transformation, let's try to go from the previous graph to this current graph. So the previous graph went like this, 4, 2, 1, like this. So that was the original shape of the 1 over 2 to the power of x graph. Now let's do some transformations. I think the first one we can do is the vertical stretch by a factor of 2. So that means that my new graph will be like 8, and this one was 2, so that now it's 4, and 1, now it's 2, and 1 over 2, now it's 1, 1 over 4, now it's 1 over 2. That's after the vertical stretch, so that's done. Now we need to do a horizontal stretch by a factor of 1 over 2. So it means that everything will be moved inwards by a factor of 1 over 2. So my next graph will be this one over here. Negative 2 became negative 1. Negative 1 became negative 1 over 2. 0 is still 0. 1 became 1 over 2. And 2 becomes 1. So I think the graph will look something like this. I'll erase the ones that are in the previous graph. So the horizontal stretch is done. Now let's do the vertical reflection, which means I'm going to move the positive values to negative values and negative values to positive values. So I think my positive 8 will become negative 8, and my positive 4 will become negative 4, and positive 2 will become negative 2, positive 1 will become negative 1, positive 1 over 2 becomes negative 1 over 2. So that's after the vertical reflection. There is no horizontal reflection, so let's move on to the vertical translation by a factor of 10. So now it means that I'm moving up by a factor of 10. So my final graph will look like this was negative 8, so after translation it's positive 2. And this is negative 4, so after translation it's positive 6. And I think I'll need to move a bit further up. Negative 2 becomes positive 8. And negative 1 becomes positive 9. And negative 1 over 2 becomes positive 9.5. And also, there was the horizontal asymptote, right? That horizontal asymptote was at y equals 0. So it means that after the vertical translation by a factor of 10, my new horizontal asymptote will be at y equals 10. So if I connect the points, now it looks like this. Okay, keeping that in mind, so the key points are negative 1, comma 2, negative 0.5, comma 6, 0, comma 8, and 0.5, comma 9, and 1, comma 9.5, and y equals 10 as my um, horizontal asymptote. And the intercept that was important was positive 0, comma 8, right? Was my vertical intercept, sorry, y-intercept. So I labeled the y-intercept as well as the horizontal asymptote. Now we don't have the horizontal intercept, so let's try to quickly find that. How do you find the horizontal? Sorry, how do you find the x-intercept? Well, it's simply it means that y value is equal to 0, right? So let's solve this equation. I'm kind of touching into the next section, anyways, but it's okay. So I think I can do minus 10 on both sides. I can divide it by 5, divide by negative 2 on both sides. So at this point, I realized that I do not have the ability to put them into the same base, right? Like the right hand side has a base of 1 over 2, and the left hand side has a base of 5, and that we can't match them together. So it means I can't solve it algebraically. Once again, for this chapter test, I'm not going to give you any questions where you need to solve such problems. In chapter 8, we'll have the ability to solve this problem, so we'll leave that on for later. Now, moving on to the next problem. So in this section, we're learning about the special exponential functions, such as half-life functions, as well as the natural exponential functions. So let's use those two to model these problems here. Model the radioactive decay of an element with initial mass of 5 kilograms and the half-life of 20 days. So using the same model that we have before, A value represents the original mass and H represents the half-life. So it means that A is going to be 5 and the half-life is going to be 20. So I think that's pretty simple. M of T will be A 5 multiplied by 1 over 2 to the power of T over 20. Now when you solve this problem, this is already complete, right? When you do the order of operations, the 1 over 2 to the power of T over 20 happens first. before you do the multiply by 5. So at this point, we don't have to multiply 5 and 1 over 2 and get 5 over 2. That's impossible. So let's not do that. And my final answer is just as it is. M of t is equal to 5 times 1 over 2 to the power of t over 20. Next problem. The atmospheric pressure in terms of elevation shows an exponential decay. The pressure at sea level H equals 0 is 1013 HPA. And the decay rate is negative 0.000128. Model the situation using the exponential function and estimate the atmospheric pressure at the peak of the Mount Everest at H equals 8,848 meters. So this seems like the natural exponential functions, and we just need to plug in the values as well. We know that A, the initial amount, is 1013, and we know that the K, the grow and the decay rate, in this case, the decay rate, because it's negative, is going to be negative 0.000128. So I think the equation would be the y equals 1013 multiplied by e to the power of negative 0.000128 x, where maybe we can change the 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 variable names. P pressure is equal to 1013 times e to the power of negative 0.000128 h, where h is the meter from the sea level, the elevation from the sea level, and p represents the atmospheric pressure. So that's the exponential function that we use to estimate the atmospheric pressure at H equals 8,848. So we just need to plug in the values. P equals 1,013 times e to the power of negative 0.000128 multiplied by 8848. Let's use the calculator for that. So this one you don't need to use a graphing calculator. You can just use the graphing scientific calculator. 1013 multiplied by, and for E, you just have to go to the ABC, and E is already predetermined to the power of negative 0.000128 multiplied. Let's use the brackets here. Multiplied by 8848. Close bracket, and I got P is approximately 326. So it shows that the atmospheric pressure did go down as you went up to the Mount Everest. Right, moving on to the next problems. Now we need to solve exponential equations. So in this, the examples that I put here are the questions that can be solved algebraically. So we're going to focus on the algebraic technique because the graphing, the one that requires a graphing calculator, will not be put on the test, and we'll learn better and more advanced skills in chapter 8. So let's solve these problems. The first thing that we need to do is identify the similar basis. To identify the similar basis, it's kind of like finding the lowest common multiple of two numbers. Kind of like that, right? When you have a number like 12 and 16, well, we think about it, and the lowest common multiple of these two numbers will be equal to 4, because 4 times 3 is 12, and 4 times 4 is 16. Something like that. We're going to find the you're going to find the common base of the two bases that we have. In this case, we have 4 and 8 as two bases. So I'm thinking, is there a number that is a power of another number to represent 4? And that same base, the power of another number, is equal to 8. I think that 2 is the one, because 4 can be represented as 2 squared, and 8 can be represented as 2 cubed. So it means that I'm going to switch each 4 and 8 into the 2 squared and 2 cubed using brackets. So it means that 4 is rewritten as 2 squared, bracket to the power of x minus 1, and 8 is rewritten as 2 to the power of 3, brackets to the power of x plus 2. Now, using the law of exponents, where when you have the power of a power, we multiply the two powers, right? So it means that my next line would be 2 to the power of 2x minus 2. I multiply 2 by x minus 1. And then to the power of 3 to the power of x plus 2 will be to the power of 3x plus 6. I multiply 3 and x plus 2. Now that the bases are same, then the only part we have to do is just solve the upper powers. So now it's going to be 2x minus 2 is equal to 3x plus 6. Now we solve it. Negative 8 is equal to x. So x is equal to negative 8 is my final answer. And of course, after we solve the equation, the good thing about the solving equation is that we can check the answer. So you can plug in the values, negative 8, to both sides of the equations and show that the left-hand side and right-hand side are indeed equal to each other. Let's try the next one. The next one doesn't seem so obvious at first sight. Well, what number to the power of what is 1 over 3? And also, what number to the power of what is 27? Now, here's a little catch that we need to be careful about. When you have a fraction like 1 over 3, we can see it as a reciprocal of a number, right? 1 over 3 is a reciprocal of 3, and we know how we can reach the reciprocal by doing a power of a negative number. So it means that my 1 over 3 can be reached by 3 to the power of negative 1. And 27 is obviously 3 to the power of 3. So now we know that the common base would be 3, because left-hand side can be represented as 3 to the power of negative 1, and the right-hand side can be represented by 3 to the power of 3. So let's continue from there. 3 to the power of negative 1, bracket, to the power of 2x minus 1, is equal to 3 to the power of 3, bracket, to the power of x. So using the same exponent laws, the power rule, 3 to the power of negative 2x plus 1 is equal to 3 to the power of 3x. Now, like before, we have the same base, so let's equate the powers. 2x plus 1 is equal to 3x. So negative 5x is equal to negative 1. So therefore, x is equal to 1 over 5. Is my final answer. Once again, we can check the answer by plugging in the values and seeing that the left-hand side and right-hand side are actually equal to each other. All right, moving on. Geometric sequences and series and the infinite series. The first question for each section will be extremely simple, because I give you the first term and I also give you all the subsequent terms. So the only thing we need to do is just identify the first term and find the common ratio. So let's find the common ratio of the first sequence. 81, comma, negative 27, comma, 9, comma, negative 3. So in this case, what we have to do is we need to find the ratio of two subsequent terms. So I think the first two terms will be great. I'll do negative 27, which is the second term, divided by the first term, 81. So we always want to divide the next term by the current term. That's going to be, after simplification, it'll be negative 1 over 3. I can do the same thing, by the way. 9 divided by 27, which is also going to be negative 1 over 3 as well. So I know that the common ratio is negative 1 over 3. Now I know the common ratio, and I also obviously know that my first term is 81. Let's put them into the formula. Then un is equal to u1 times r to the power of n minus 1. So my un is equal to 81 times negative 1 over 3 to the power of n minus 1. So there's no need to simplify it any further from here. 81 tells me, oh, that's the first term. And negative 1 over 3, oh, that's the common ratio. So that's it. The next problem is not so obvious because I gave you the first term, but finding the common ratio seems quite more difficult because you don't see the two subsequent terms right away. So let's put this on a sequence pattern instead of saying u1, u4, blah, blah, blah. Okay. So what I'll do is I'm going to put them as, well, first term is square root of 5, comma, and then there's a blank, my second term, and then there's a blank for my third term, and then there's 25 for my fourth term. Well, so what do I know? So I know that from square root of 5 to 25, I'm going to multiply by the common ratio, not once, not twice, but 3 times. So I know that my 25 will be equal to square root of 5 times r times r times r, which is 25 is equal to square root of 5 times r to the power of 3. By the way, I could use the formula as well, because u4 is equal to u1 times r to the power of n minus 4 minus 1. So then u4 is equal to 8, square root of 5 times r to the power of 3. So you get the same idea. u4 was 25 here. So now let's try to solve this equation. How do I do that? Well, I think I'll have to use the calculator here though, because if I divide both sides by square root of 5, it becomes 25 divided by square root of 5 is equal to r cubed. Now let's do the cube root on both sides. I'll use the calculator for that. Cube root of 25 divided by square root of 5 is approximately equal to 2.24. Now, here's a little hint. I have a feeling that this number might be a square root of something, and that's why we have this irrational number. So maybe I can try to assume, hey, like, what if I square both sides? So let's try to square this entire thing and get 5. Apparently, r squared was 5 using the calculator, or 2.24 approximately, squared was 5. Then what can I conclude about actual r? My r value will be square root of 5. And of course, I can check that. Square root of 5 times square root of 5 is 5. 5 times square root of 5 will be 5 square root of 5. And 5 square root of 5 times square root of 5 will be 5 times 5, so that's 25. So we know that we got the right answer here. Now let's also find the sixth term. Now that we know the r, and we all know the u1, I think I can plug into the formula. Un is equal to u1 times r to the power of n minus 1. So my un is equal to, um, I'm trying to find u6, right? u6 is equal to, u1 was square root of 5, r was square root of 5, n is 6. It means that u6 is equal to square root of 5 times square root of 5 to the power of 5. So I think in total we have square root of 5 6 times. Trying to solve this without the calculator. 6 can be rewritten as 2 times 3. So I think I can write it as 2 times 3. It means that square root of 5 squared to the power of 3 using the laws of exponents. So therefore u6 is equal to 5 to the power of 3, which means that u6 is equal to 125. Of course, we can use a calculator if you want. So I found the r and the u6 in exact values. Let's move on. So I strategically put the same questions here, similar patterns here. So we already know the formula for the un, we know the u1 and the r for each case. So let's just write them down. u1 for the first one was 81, and the r was negative 1 over 3. u1 for the second sequence was square root of 5, and the r was also square root of 5. Now let's use the formula for the geometric series to find the sum of the first 6 terms. So how do you find the sum of the first 6 terms? Well, we use the formula Sn is equal to u1 times r to the power of n minus 1 divided by r minus 1, and apply 6 for n. In this case, u1 was 81, r was negative 1 over 3. So I have a strong feeling that I need to use a calculator for this problem. So I'm just going to put this entire thing into the calculator as it is. 81 times bracket negative 1 divided by 3 close bracket to the power of 6 minus 1 close bracket divided by bracket negative 1 divided by 3 minus 1. And I got 60.6 repeating. And I think if I just press the fraction button, it turns out to be 182 divided by 3. So the sum of the first 6 terms is equal to 182 divided by 3. Let's do the same thing for the second question. The formula is Sn is equal to u1 times r to the power of n minus 1 divided by r minus 1. So S6 is equal to square root of 5 times square root of 5 to the power of 6 minus 1 divided by square root of 5 minus 1. So same thing, let's just put it into calculator. Square root of 5 times bracket square root of 5 to the power of 6 minus 1 close bracket divided by square root of 5 minus 1. I got S6 is equal to 224 point, approximately 224. At this point, because I know that I added the square roots, I'm not going to bother finding the exact values of it. Right, last problems. Infinite geometric series. So one thing to watch out for when you're doing the infinite geometric series problem is that we need to make sure that the common ratio or the absolute value of the common ratio is less than 1. If it's not less than 1, we can't use the formula at all. So let's first identify whether if we're allowed to use the formula or not. In the first sequence, the first term is 81 and the common ratio is negative 1 over 3. In the second sequence, the first term is square root of 5 and the common ratio is square root of 5 as well. So the first one, the absolute value of r is positive 1 over 3. And positive 1 over 3 is definitely less than 1. So it means that we can use the formula. We're allowed to use the formula here. What about the second one? The absolute value of r is equal to square root of 5. Square root of 5 is greater than 1. So are we allowed to use the formula? No. So we're not going to find the formula here. We're not going to use the formula here. So let's find the sum of all terms of the first sequence. S infinity is equal to u1 divided by 1 minus r. So that's equal to S infinity is equal to u1 is 81 and r is negative 1 over 3. Which is 81 divided by 4 over 3. So I think it'll be, 243 divided by 4. So I know that sum of all terms of the first sequence will be 243 divided by 4. What about the second one? Find the sum of all terms of a geometric sequence with r equals square root of 5. Well, this one, it doesn't exist because the common ratio is square root of 5. There is no infinite geometric series. Or we can also say the sum diverges. Right, so that's all the problems in this worksheet. Hopefully this video helps you out with the preparation for the Chapter 7 test.